Hi guys, this is the first video on the new account. I'll be using it to post chemistry content, so stuff like this where I teach you the content, and then after this we'll do some revision, and then I'll be doing some HSC questions too. Main purpose of this is not to teach you fully, but just so you have an understanding so you can go into class and know what's going on. So I'll be covering module 5 today. Not the whole thing, of course. We have to split it up into multiple videos, but basically it's about equilibrium reactions. So there's 4 topics, actually 3 in the summary, but I'll be splitting up into 4 videos. So we have equilibrium, systems, qualitative and quantitative, and summary. So I'll be covering equilibrium systems today. It's half of it is a revision from year 9 and 10, so it should be pretty straightforward. And there's only like a bit of new content to learn. So there's 3 subtopics in equilibrium systems. There's chemical systems, irreversible and reversible reactions, and a static and dynamic equilibrium. So let's cover chemical systems first, which is basically a revision from year 9 and 10. So we all learn about open systems in year 9 and 10. They can freely exchange matter and energy with the environment. You know, like in this example, right, the heat energy is being transferred and the water vapor is escaping too. So this is an open system. In a closed system, you can exchange energy, but not matter. So in this case, the pot is closed. The heat can escape still, but the water vapor can't escape this time. It's different. The last system is an isolated system, and it can't exchange matter or energy with the environment. So there's actually no perfect example of this, but just for simplicity, we have a thermos. You know, the water can't escape because there's a lid, and also, you know, the heat can't escape because it's insulated. So yeah, those are the 3 types of systems. Next, we'll be moving on to irreversible and reversible reactions. An irreversible reaction happens when both drivers are either favorable or unfavorable. What does this mean? That means that there's either 2 cases. So delta H is either favorable and delta S is also favorable, or delta H is unfavorable and delta S is also unfavorable. Now, they also go to completion. So in this reaction, right, the combustion of ethanol, all the reactants will be converted to product at the end. There'll be no reactants left at all. So that's why we represent it with a one-way arrow, because it doesn't go both ways. So we use only a one-way arrow. In this reaction, you can see that, well, for combustion, right, the delta H is always negative, and this is because, you know, the products are more stable than the reactants. So on an energy profile diagram, you know, like one of these, the reactants are here, the reactants are here, and the products are here, right? And this is the energy. See how the products have a less energy than the reactants? That means that it's a more stable state. And when the bonds form, they release energy, and this creates an exothermic process. So for this, we have delta H is negative. Now we look at the number of moles converted to look at entropy change. There's 1 mole of liquid. There's 3 moles of gas on the reactant side. And it's being converted to a total of 5 moles of gas on the products. So this is quite obvious. You can tell that it's increasing in disorder. So therefore the entropy change will be positive. Now, since both drivers are favorable, this reaction is, you know, spontaneous at all temperatures. So no matter what temperature it is, as long as it passes the activation energy, it will happen without any continual input of energy. So like the reverse example is if both drivers are unfavorable. So like, say photosynthesis, so you have CO2 and water transforming into this glucose. Right? you can see the entropy drive is negative because you see there's liquid and gas on this side, and this side's converted to solid. And you know, like the coefficient is less, and plus it's in a lower state of entropy. It requires the input of sunlight, so light energy, right? That's why it's endothermic, because you know you need the sunlight to make the reaction happen, and therefore like delta H for this is really positive and delta S is really negative. So it's completely unfavorable, and it's not spontaneous at any temperature. So the reason why these can't form equilibrium systems is because the reverse reaction for one of these reactions will be unfavorable and non-spontaneous at any temperature, while the forward reaction will be spontaneous at any temperature. So it can't happen in conjunction with each other. Now, when you look at reversible reactions, there's one clear difference. The drives oppose each other, and this allows the reversible reaction to happen. It can happen in both forward and reverse directions, and you represent it with this arrow. So like you draw it like this, yeah? It just shows that the products can form reactants and the reactants can form products. So for this one, yeah, the thermal decomposition of copper carbonate, the delta H value is negative. It is endothermic. Oh. Yeah, because you need heat to decompose this thing. However, the entropy drive is positive because you see like 1 mole of solid converted to 1 mole of solid plus 1 mole of gas. If you cancel these out, you have 1 mole of gas. And you know gases are the most disordered, so it is an increase in entropy. Since the delta H is positive and the entropy is favorable, what would the reverse reaction be, right? The reverse reaction will have an exothermic delta H, but an unfavorable entropy. So, what happens when two drives oppose each other? What happens to the delta G? This determines how spontaneous a reaction is. Well, it depends on the power of the drive, right? And it all depends on the temperature to see if it's spontaneous or not. So, for these types of reactions, an equilibrium can form, mainly because when you reverse the reaction, it's not going to the extremes. And yeah, I'll cover that in a bit. But yeah, just know that it is possible for an equilibrium system to form only if it's a reversible reaction. So an equilibrium system, as we stated before, it's a reversible reaction. It has to be. The reaction has to be spontaneous under the same conditions. So it just has to happen. Like it has to be at a constant condition, and both reactions has to be able to happen at the same time, you know? And in an equilibrium system, the forward reaction rate is equal to the reverse reaction rate. It has to be a closed system, otherwise in an open system, matter is leaving, right? So if you look at this example, what happens if this is in an open system? Like all the gas is just gonna leave. So then you won't have any of this, and you need that to produce copper carbonate. That's why it has to be a closed system. In an equilibrium system, you won't be able to see any microscopic changes either, but there will be microscopic ones going on. Now, there's two types of equilibrium systems. We'll cover both, but we're only really going to be tested on dynamic equilibrium. So the first one is static. It's a state of equilibrium in the sense that nothing is happening at all. So the reaction rate is 0 for both forward and reverse. It usually happens for irreversible reactions, and you know you can't see microscopic or macroscopic changes because nothing's happening. So an example would be, you know, like the combustion of ethanol, right? Because, you know, like everything's converted to products. There's nothing left here, right? Or just like, I don't know, like if you try to recreate photosynthesis in a lab, it just doesn't happen, right? So there's no products. The main type of equilibrium system that we're covering in Mod 5 is dynamic equilibrium. There's a lot of examples of this. So for dynamic equilibrium, the rate of the forward and the reverse reactions is positive and equal, so it's not zero. The rate is equal, so at the rate that products are being produced, reactants are also being produced at the same rate, and both reactants and products have to exist and interact in this system at the same time. By the way, this also has to be under the same conditions, and the concentration ratio will be constant at a constant temperature, which I'll cover more when I do quantitative equilibrium. And like, this can only occur when these are all satisfied, right? Because this is what you need for an equilibrium system. So yeah, you need this to happen in an equilibrium system, and you can't observe any macroscopic changes, but there are microscopic ones, because reactants are being converted to products and products are being converted back into reactants, right? Now, this example, it might sound a bit strange, but it's a good example because, like solid salt, right? What happens when you dissolve it in water? It dissolves, but to what extent, right? After it reaches like 36 grams per liter, that's like the maximum solubility. So after that, we call it a saturated, right? What happens when it's saturated? It looks like nothing's happening because you add more in and it's not going to dissolve, right? But the thing is, right, this reaction is actually happening at the same rate, forward and reverse, but you can't notice. The solid you add in is being converted into ions, right? However, the ions are also precipitating out at the same rate. So that's why you can't see any changes, but there are changes happening. And this equation demonstrates what's going on inside the system. Okay, so that's basically it for this video. If you guys have feedback, comments, if you want to see anything, any topics, just let me know in the comments. So next lesson, we'll be doing qualitative equilibrium, that's collision theory, KQ, Q, and how to analyze equilibrium graphs. So yeah, thanks for watching. Yeah.